So welcome back, everybody, and welcome to this session on quantum computing and quantum machine learning. The topic today is a continuation from the lecture from last week, where we now are going to summarize some of the discussions we had on quantum Fourier transforms. We are going to repeat some of the examples so that you get a better feeling of how we actually build up a circuit which now represents a quantum Fourier transform. Now, when you have the quantum Fourier transform, of which you can also find the inverse Fourier transform, so these quantum Fourier transforms are, in essence, they are unitary transformations, so that we have the inverse that exists. We can then use that one in the next step, which is the so-called quantum phase estimation algorithm. And we are going to go through derivations of the quantum phase estimation algorithm, which is going to involve the quantum Fourier transform. Now, these elements are also elements in something which we will only at the end briefly discuss, which is called Shor's algorithm. And this is a very famous algorithm which demonstrated the capability of factorize in a much more efficient way than you have in standard factorization algorithms. This obviously requires some more insight about the number theory, and it forms also one possible variant, or an optional one, for the second project. 1 and 2 are, however, the elements which define the second project, and you should feel free then to either modify these elements or also to add things like the results from the first project where we discussed the operational quantum eigensolver. So to quickly remind you, so the quantum Fourier transform, as I said, is a key component in many quantum algorithms, and it is a much more efficient way to perform the Fourier transform due to the fact that we utilize superposition and entanglement compared with a classical discrete Fourier transform or its fast variant, which is the fast Fourier transform. And this is essentially due, as we said, to entanglement, quantum parallelism, and superposition, although we do have superposition in a discrete Fourier transform. So what we have in the classical case, with a discrete one, we would have n points. These can be complex numbers. And the discrete Fourier transform is typically written in terms of this series. So the inverse transform for this x of n is then given in terms of these elements x of k. And then we have the exponential, which then encodes the linear superposition of the data sets x of k. This is something which we last time, and also the time before, we rewrote in terms of a matrix form. So we would have a matrix F whose elements, j of k here, are then represented by this explicit term. And this matrix here is something which we then can multiply with this vector x. In the quantum Fourier transform, what we have is that n now is represented by the number of qubits, so 2 to the number of qubits. So these are binary events. So we have either 0 and 1. So that means that to the power of 2 and n, this gives us a total number of arrangements which we can have. And this transforms the classical Fourier transforms into a quantum Fourier transform. And what we're going to do today, besides reminding ourselves about the some basic examples, which then give us an intuition on how we build the circuits, is also to see how we can implement this numerically. So the classical fast Fourier transform runs actually in terms of this number n as n times log n. This is a typical number of floating point operations, whereas the QFT would then run like n squared here, which then gives us a much smaller number of gate operations. And that's a clear improvement compared with the classical algorithms. So these matrices, as we discussed last time as well, are unitary. And last time we actually proved that. And that guarantees that the QFT is a valid quantum operation and it should preserve norm, and it is reversible. So before we dive into the codes here, I actually wanted to remind you a little bit about some simple examples and how we end up setting up the circuit for a quantum Fourier transform. And the simplest case to start with is a case with just 2 qubits. So I'm going to switch to the whiteboard, and let's do that. And then return to the notebook here, to the Jupyter notebook, when we are going to look at codes. And there's a penny lane code, and I need to explain to you some of the basic settings here and how we actually implement these quantum circuits for a Fourier transform. So let's go back to the Jupyter notebook. Now the whiteboard, and remind ourselves of some simple examples which we discussed last time as well. Now the basic Fourier transform, when we set it up, this quantum Fourier transform is something which runs like as follows. So the basic Fourier transform, when we act on a set of states, so we would have something like a QFT here. So that's the Fourier transform. And this acts on a given state with a bit either 0 and 1. So this would be the first one, the second one, and then up to n-1 qubits. And all these x's can take values 0 and 1. And what we found last time is that this, when we used a binary representation of floating point numbers, and today in the example, we're actually going to look at a simpler case, which is the integer representation. We end up with 1 over the square root of 2 to the power of n. So this is the number of possible states we can make. And then we had a series of tensor products. So we have 0 here, plus e to the 2 pi I. And then we had this compact notation now where we represent the bits as a floating point binary representation multiplied with state 1. And then we had a tensor product of 0 plus e to the 2 pi I and 0, x0, x1 multiplied with 1. New tensor product, and this continues all the way down to the last one. And then we would have a 0 plus e to the 2 pi I of 0, x0, x1, up to xn minus 1. And this Fourier transform, we can obviously perform the inverse of that one. And then if we do the inverse of that state here, if we actually act with this with a unitary transform of that, then we would get back this state here. But let's now try to break it down into a system of just 2 qubits, just to remind ourselves about these technicalities. So let's take the n equal 2 example, which we went through last time, and just remind ourselves a little bit, because that's very convenient when we are going to look at the codes. So in order to understand it, we are just going to break it down. And that means that we are going to have 4 states. And the first one is just the tensor product of qubit 1 with qubit 2. And we would often rewrite this as state 0, and with a subscript 2 here to indicate that this is just a system which is set up of 2 qubits. But normally, we will simply just revert to this notation here if we don't lose the general aspect of the system we are looking at. So if everybody knows that this is a 2 qubit system, this 0 refers to state 0. And then what we have is the next set of states, 0, tensor product with 1, which we would write as state 1 in this space, or simply just 1. Then we have 1, 0, and then we have 1 tensor product with 0, which then becomes state 2 here in this space. And then we have the final one, which is 1, 1, which is just 1 tensor product with 1. And this is state 3. Now, one way, as we discussed last time, to encode this information is to use an integer representation of the bits. Alternatively, as we did in the compact way last week, is to use the floating point representation of a bit. Now, a given state, if we now look at a general case for this 2-qubit system, so if we have a system like this would now just represent some x0 and x1, which we haven't specified. So x0 and x1 could be 0 and 1, obviously. And we would have another basis, which is composed of these 2 qubits, which now contains y0 and y1. Now, in this standard algorithm, as you will see, when we now perform the operations and write everything out in terms of specific gates, which in our case are going to be Hadamard gates and rotation gates, then when we do the operation, if we have a system where we have qubit 1 and qubit 2, the output will typically reverse the order of the qubits. And if we want to stick to this kind of nomenclature where the first qubit is given by y0 and the second one by y1, similarly with x0 and x1, then we need at the end to introduce what's called a swap gate in the circuit. We are coming back to that. Now, if I'm just setting up the Fourier transform, then the state x2 in terms of the basis y is going to be given by 1 over 2 to the power of 2 square root. So that's obviously 1 over 2 here. And then we are going to sum over the states y0 up to 3. And then we have the exponential of 2 pi I and x and y. And this is divided by 2 to the power of 2 and multiplied with y, not y2, but y. Let me just cancel that one. So we have this one, and then it's y in this space 2. So keep in mind now that this states x with subscript 2 and y with subscript 2 are actually 2 qubit states. And what is convenient to do now, when we now look at the state x2 here, which we defined at x0 and x1, the way we can find this number here is actually by setting up a simple recipe where we have 2 times x0 plus x1. And we would obviously have the same for y. So in the sum here, we are now running over the states. So we decided that state 1 is, the first state is this one we labeled with 0, 1, 2, and 3. So the sums here run over these labels 0, 1, 2, and 3. But then when we are setting up these operations, we're actually going to break down everything in terms of operations on single qubits. So that means that when we now are going to set up everything here, because this is nothing but what we would have for a classical discrete Fourier transform, what we need to do is actually to break this down in terms of actions on single qubits, and then we can set up a circuit which, as you will see, will be composed of a Hadamard gate and a rotation gate. Let's try to see that now. But before we do that, let's just convince ourselves that this algorithm here gives us these labels which we have chosen. So this is just an internal labeling which we choose, which is going to make the calculations more efficient. So we see now that if we have the state 0, then that simply corresponds to 2 times 0 plus 0. So this is the qubit x0 and x1. And this applies also to y0 and y1. So there is no need to write a similar example with y's because we just get the same. So we get 0. If I take the next one, you see then that what we would have is 0 times 2 plus 1, which is 1. And then we take the next one. So that would be 1 times 2 plus 1. And that gives us 2. And the final one is 1 times 2 plus 1, which gives us, so sorry, this should be plus 0. And this is equal to 3. So that fits. Now, if I do that, it means that when I look at my exponential and the argument in the exponential, I have 2 pi I xy divided by 2 here. And I can break this down. If I now look at this term, just look at the argument. So the argument can then be written as 2 pi I, and this is obviously divided by 4. And then I have 2x0 plus x1 and 2y0 plus y1. So I'm simply using this simple formula which we used here to find the right labels, and I'm simply rewriting the x and y's in terms of the individual qubits. So in that specific case, we can then rewrite this argument. So that becomes simply 2 pi I, and then with a simple rewrite, I have y0, x0 plus x1 divided by 2, and then I have plus y1. And the reason why I'm doing this is I want to split the summations into a summation of a y1 and y0. And just remember now that y0 and y1, and the same with x0 and x1, they take values which are either 0 or 1. So that applies to both cases. So when I now rewrite this formula, it's useful to note that when I take the exponential of x0, if you look at the products here, if you look at this term here first, y0 and x0, multiplied with 2 pi times I, this term here will either give us 0 or 2 pi times I. So if x is 0, then obviously we have 0 as argument to the exponential. If y is 0, get the same. If y0 and x0 are 1, then we have 2 pi I. The exponential of 2 pi I just gives us 1. So this is just an intermediate thing to note. So I'm just going to frame it in. Note that. So we have e of 2 pi I of x0 of y0 is always equal to 1. So we can simplify the expression then, so that we can then write everything when we now are breaking it down in terms of each individual qubit. We can now write the sums down as follows. So we would have 1 over square root of 2, and then I have a sum over y0 equal to 0 to 1. And then I have my exponential, which now, since one of the terms just gives us 1, we can just leave it out. So we have y0 times x1 divided by 2 here. This is multiplied with 1 over 2 square root of 2. And then I have y1 equals 0 to 1. And then I have the exponential of 2 pi I times y of I multiplied with x0 divided by 2 plus x1 divided by 4. And this is finally multiplied with y0 and y1. And just remember now that these two guys are actually y0 tensor product with y1. So that means now that when you look at the expressions, we will have one part here which acts on this guy only. So we could, in principle, just rewrite this expression, which we have now broken down as a sum over y0 and y1 instead of a sum over y, which run over all the 2-qubit states. We now could actually just take this one and plug it in here, y0, but then we would need to have the tensor product here, and then we would need to have y1 here. So there should be an end of parenthesis here as well. Okay, so clearly, when we now look at these expressions, if we now look at the first term and just leave the next term unchanged, there is an operation on the first qubit. And that first operation, when we now look at it, so if we now look at 1 over square root of 2, and then we perform the summation, we're actually going to get 0, because this is acting, so this is the first term, plus e of pi I multiplied, and then we obviously have y0, and in this case y0 is equal to 1, multiplied with x1 times 1 here. So this is a very useful result here, because we know that the e to the pi of I takes a specific value if this y0 is equal to 0. So suppose now that we only have y0, if x is 0, sorry, not y0. So if x1 is equal to 0, then we know that what we have here gives us simply 1 over 2 pi of 0 plus the state 1. So this would be how the first qubit changes from the first term. Now, if x1 is equal to 1, we get e to the pi I multiplied with 1. So that gives us minus 1. So in that specific case, we would have 1 over 2. So this is all from the first qubit. So plus 1, actually it's a minus 1 here. So when we look at these operations, we need to multiply with the second term. So we do actually have a tensor product then. And this tensor product runs like 1 over square root of 2. I have the sum over y1 equals 0 to 1. And then I have the exponential of 2 pi I yi and y1, sorry, x0 divided by 2 plus x1 divided by 4. And this is multiplied with qubit y1. So if you look a little bit closer at what we have here, depending on the incoming qubit, so whether we have x1 equal to 0 or x1 equal to 1, that means that what we are going to see then is the operation of a Hadamard gate on the first qubit. So that specific operation which we see here is something which we then can encode, since we have 2 qubits. So this is nothing but a Hadamard. It's a Hadamard operation. On the first qubit. So if we then think back of the Hadamard, so this Hadamard is nothing but 1 over square root of 2, and then we have 1, 1, 1, minus 1. So if we are acting on a state which is in state 0, then we simply get a linear combination. So H, just to quickly remind you of that is simply as the same as 1 over square root of 2 of 0 plus 1. So it's the way we make a linear superposition. And if I act on this, then I have with the state 1, then we have 0 minus 1. So what we could do then, if we think of the first operation, so the first term in that sum is equivalent to us having a Hadamard gate, a Hadamard matrix, a 2 by 2 matrix, and then tensor product with the identity matrix, which now acts on the second qubit. And this will then be multiplied with y0 and y1. So nothing happens with y1 in this specific case. So that's the first operation which we can now rewrite as a Hadamard gate, which now acts only on one of the qubits. We would typically write that in the following way. So we have an incoming qubit, which we leave unspecified, and then we have a Hadamard gate, and this produces a new state. So we have an initial state, which we just leave unspecified, psi0, and then we produce a state psi1, where psi1 here is simply H acting on psi0. Now, what's useful to now is to take a look at the second term, because then we can quickly see what kind of gates this will correspond to. So the second term, which we had, reads as 1 over square root of 2, and then I have a sum of y1 equals 0 up to 1. And then we have the exponential of 2 pi I of y of I of y1 plus x1 divided by 4 here. And this term actually acts on the second qubit. So if I now look at the first term, so I can rewrite this as 1 over square root of 2 here, and then I have the sum of y1 equals 0 up to 1, and then I have an exponential of pi I, no, y1 multiplied with x0. And then we have the next term, which is an exponential, which now contains pi of I multiplied with y1 and x1 divided by 2 and multiplied with y1. So let's now take a closer look at the two terms, because you can think of these as two operations which are done on this specific qubit. And remember also that this term needs to be taken together with the first qubit, which we have here. And we need thus to have a tensor product of these two states, which means that the output of this one needs to be tensor producted with the first qubit. But let's now take a look at what happens here. So now we are mixing the second qubit, y1, with the first qubit for this x0. This is also one of the reasons why these operations are going to flip the order of the qubits, which means that at the end we need to insert a so-called swap gate. But let's take a closer look at this term. So this term is nothing but what we had earlier. If we go back here to the first term here, so that means this term here. This is nothing but a Hadamard gate. So let's just single that one out. So this one will be nothing else than a Hadamard gate. On the second qubit. On the other hand, when we now look at this term here, we are going to identify this one as a rotation gate. And the more of these we have, that means the more qubits we have. If we had 3 qubits, there will be a y1 multiplied with x2 divided by 4. That would be a further rotation matrix. Now, since we have 2 qubits involved, this is going to correspond to a control S gate or just a controlled phase gate. But let's now look at this rotation gate and how we typically would define it. So just to give a quick reminder. So the rotation gates are defined if we think of this as a 2 by 2 matrix, by 1, 0, and then we have 0, and e to the 2 pi I divided by 2 to the power of k. So in our case, we have k equal to 2 because we have the 2 qubits case. And that is going to give us, in our case, so here, with 2 qubits, n equal to 2, then we are going to have e to the pi I divided by 2. And we know that that is equal to I, the imaginary number. So what we would need to do then is actually to set up what is called a control phase gate or CS gate. And that CS gate is going to be given by 1, the identity matrix, and then the tensor product of that one with this rotation matrix. So that specific matrix is going to look like as follows in our case. So that will look like as 1, 0, 0, 1, and then we have 0, 0, 0, 0, 0, 0, 0, and then we are going to have a 1 here, 0, 0, and then we will have, in our specific case, pi I divided by 2 here. So that would be the control S gate. Now, finally, what we will also have is an operation on the second qubit, which is going to be given by a standard Hadamard gate. So this last term, which you see here, that will simply take the form of the identity matrix, which acts on the first qubit, multiplied with a Hadamard gate. So if we then want to set up everything, what we end up with is the following. So we will have a transformation, a QFT, which is equal to the following matrix, where we have 1, 1, and we actually could get this one by simply doing the mathematics of a discrete Fourier transform. And we had that some weeks ago. 1, 1, minus 1, minus 1, and then 1, minus 1, minus I, and I. And just keep in mind that this is going to be, since this is the last one, so we have a Hadamard gate, and then we have this control S gate, and then we have the Hadamard gate acting on the first qubit, and tensor product with the identity matrix. So when we now set this up as a circuit, this is going to look like as follows. So we will have an initial state, which we just label as a phi 0. Then, let me just make this a little bit shorter here. So on the first qubit, we have then a rotation, H. No, not a rotation, but a Hadamard gate. So this could now be our state, x0. This could be the x1. And then what happens next is that we have the control S gate. So this is normally just written like a CS, or since it's acting on one qubit, you will often see this one as just a rotation gate. So we would have an RK here. And then finally, we have a Hadamard gate, or Hadamard operation on the second qubit. So this gives us a state psi1. This gives us a state psi2. And then finally, we have the final state psi3, which is now the Fourier transform of a state x0, x1, which is now Fourier transformed to a new state. So roughly, this is the way we would now encode a simple 2-qubit operation. We can do the same, and we did that actually last week, but we're not going to repeat that example. So you can actually look up the lecture notes from previously, where we then went through the case with three qubits. But the important point now is that these operations, which you see here, which we could actually rewrite in terms of just a matrix, like the matrix which we have here, this will be a matrix multiplied with the original vector, and that will tell us how a specific vector transforms into a new vector. So depending on the setup with the initialization of the original vector, this is going to give us a final state, which now in this specific case is going to be a linear combination of different specific states here. And you can see that if you just use an initial example. So suppose now that you take as an initial example, and let me try to find my notes here. Let me see if I can find my notes on that. Should have it somewhere. So suppose I take that matrix. Let's just now call this QFT2. So let's give it a specific subscript. So if I act on on a state, QFT2 on the state, which will be the state 3 in this basis, which is then the same as that specific matrix, 1/2. And then I have 1, 1, 1, 1, and 1, -1, I, minus I. And then I have 1, 1, -1, -1, 1, 1, minus I, and I acting on this specific state, 0, 0, 1. What I will get then is a linear combination of the given states. And you will see now in the code, which we are going to look after the break, we are going to get these different types of examples. So we have a 0, 1, we're going to have a -1, 0, and then we are finally going to have a +1 times 1 here. And you can see that immediately, because if you take, let's say, the first row, then it's the 1 here, which is multiplied with that one. So that gives us this vector. In the next case, what we will have is our next state, which will have a -1 here, minus I, multiplied with that one, and that gives rise to this state. And then when I look at my next one, this will have a -1, which gets multiplied here. So it's a minus of this state here. And then finally, the last one is just an I times this state, which just gives us this. Now, we could write this as a matrix vector multiplication, but that's not the place where we do gain efficiency. We gain efficiency when we can rewrite everything in terms of this single qubit operations. And that is one of the big benefits of setting up a Fourier transform in a quantum way. So the other thing which I wanted to quickly just remind you is that last week and also the week before, when we looked at these type of operations, we did it in a more compact way, where we had the floating point representation of binaries. Now here, for simplicity, we took the integer representation and then simply use that one in order to set up the different fractions which you have here. And each one of these terms is something which we then can interpret in terms of a specific gate. So in the first case, we could have the acting on the first qubit, just a Hadamard gate. And then for the second one, we would have first a phase gate, a controlled phase gate, or controlled rotation gate. And finally, we have a plain Hadamard gate. And that is something which we, in a compact way, can rewrite in terms of the final matrix here, then the control S, and then the initial one here. And remember now that this is the one which acts first, and that's why we have that one here. So this is this one. Then this one is represented by this specific matrix. And finally, this one is the one which gives us this one. So we have broken down something which is now a matrix which acts on a vector in terms of single qubit operations. Actually, being able to break down things in terms of single particle, single object operations leads often, actually in most cases, to more efficient algorithms. So the kind of situation which we end up with then is a case where we now have the possibility to build up a circuit. So one thing which actually happens is that the order of these qubits will be inverted. So what is common then is actually to have a swap gate at the end, and this would typically be marked with this. So all these circuits, so to bring back everything in the order, so if we have an order x0, x1, then we want to keep that order for the output as well. So we need to perform a swap operation, and this is something which is included in the codes, which we will look at after the break. So before the break, we looked at the short repetition of the quantum Fourier transform and looked at the specific case with 2 qubits. Last week, we had the case as well with 3 qubits, just to get a feeling of how we build up these quantum Fourier transforms in terms of gates. And as we said, I mean, the Fourier transform can be efficiently implemented using a combination of Hadamard gates and controlled phase gates. So the basic operation is this one, and that is achieved through a decomposition in a quantum circuit, which then corresponds roughly with n squared gates. And for the 2-qubit case, we had a 2 Hadamard gates, we had a control S gate, and then at the end we have a swap gate. So the typical operation, if we now look at the case with n equal 3, which we also discussed last week in more detail, we apply a Hadamard gate to the first qubit, we apply a controlled rotation gate, or phase gates as they often are called, to qubit 2 and qubit 3, and then we repeat recursively on the remaining qubits, and then at the end we apply a swap gate. So the controlled rotation gate in the rotation operation is simply given by this 2 by 2 matrix. And that gate introduces the correct phase into the wave function based on the binary digits of the input number, as we saw from the example before the break. So a typical circuit for 3 qubits would then be composed of first having a Hadamard gate, and then we have the control gate, and when we have a new control gate, and finally, we have a Hadamard on the second qubit and a Hadamard on the third qubit. And here at the end, we would perform a swap operation. So the swap operation is actually needed because when you do the circuit implementation of n qubit quantum Fourier transform, you find at the end a cascade of swap gates crossing qubit 1 with qubit n, qubit 2 with qubit n minus 1, etc. And these are not arbitrary X operations, but they arise inevitably from the fact, and you will see that when you run through the 2 qubit case or the 3 qubit case, is that the standard QFT, when written as a matrix, maps computational basis states into a bit reversed amplitudes. And this swap gate simply, what they do is to undo that bit reversal so that the output register has the qubits ordered in the way you have defined. So you have opted for a specific ordering. The QFT operation inverts this ordering, and then we want to bring it back. And you can see that there's some step-by-step derivations here, which I will just leave as they are. But you can obviously avoid them. In principle, yes, but in a physical device, the wiring corresponds to actually real qubit lines. And if you want the logical output bit yn minus 1 on the same physical wire as the input xn minus 1, then you must physically swap the states. So hence these swap states are unavoidable whenever you demand that qubit indices retain their original semantic meaning. Because as I said, everything you're doing now is being broken down into explicit physical operations. And you will typically see when you go into penny lane, instead of writing this as qubits, you will often see that it's written as wires, because every qubit then is something you would then represent physically as something you can label as a wire, for instance. And the typical way you would use penny lane is to start by setting up the QML device. And then you would perform the rotations here. And then you see if it's 0, then you have a Hadamard gate. and then you have the phase shift gates. And then you will see here the right indices which come in. And at the end, you have the swap registers. And in this specific case, you can then set up a given basis state, which we have set up here, and you perform the rotation. So I'm going to look at more examples below. I will just leave the penny lane example as it is. This is something you can use in project 2 if you want to. Alternatively, you can write your own code, as you can see from the examples below here, if you prefer that. Or if you want to use Qiskit, you should feel free to use Qiskit as well, or alternatively. So the QFT requires n squared gates. So if we have 2 qubits, as we saw, we had 4 gates. And the approximate QFT implementations that can actually reduce the complexity by omitting small angle phase gates. So if the angles are small, then you can actually omit them. And it's a very efficient one. The inverse and the phase estimation algorithm, which is coming later now, relies on us being able to calculate the inverse, which is easy to set up when you have the quantum Fourier transform. And in the circuit constructions, then we would typically, to reverse the QFT circuit, you swap the order of the gates, and you replace Hadamard gates with Hadamard gates, self-inverse, obviously. And then you replace each rotation gate with its conjugate transpose. That would be what essentially what you would need when you're setting up the inverse of a quantum Fourier transform. So the codes which you will see here are examples on where you can actually do this without using penny lane or Qiskit. So the code which you will find essentially have these kind of operations. There's an inverse QFT. There's a measurement sampling. So you do random draws from the initial state probability distribution. Forward and inverse QFT is built in. It uses exact Hadamard and controlled phase gates, and it simulates a quantum measurement from the QFT result. And this is essentially what you will end up doing. And then there's a bit reversal, which ensures correct output basis alignment. So all these elements are first baked into the first code here, which is just written as a straightforward program with no classes, no object orientation. And you can now see this applies a single qubit gate to the target qubit. The operations are pretty easy to follow. You have a Kronecker, a tensor product here, and then you have an applied control phase, which is the next step here. That's actually not that difficult to see. And then you have the swap register, where you swap the bits. And then you do the QFT step by step, where you run through the Hadamard gates and the control phase gates. And when you have that, at the end, you just return the swap registers. And this is where you measure the state. And in this specific case, I've taken the number of shots to be given by 2 to the powers of something. And this is 2 to the power of, what is it, 16? Yeah, I think this is 2 to the power of 16. And then we calculate the probability for finding a specific component. And in this case, we could even take a simpler case. We could take 2 qubits, and that means that the number of states is just 2 to the power of the number of qubits. And I could now say that since we only have 2 qubits, it means that we have 4 states. So I could let this be the first state. So in that case, we would now start with the state number 1, which should be 0, 1 instead of the 3 qubit case. Then I apply the step by step. This is the inverse QFT. So this is my initial state, the one I start with. So let's see what it gives us. And you can see now that the amplitudes, and if we look back at the example which we had before the break. So let's look at the example we had before the break on the whiteboard. So let's now say that the initial state is state number 3 instead. So that means that we have, let me see. Yeah, these are the QFT amplitudes, and that should be, Yeah, and we see we have the measurement, so we get a factor of a half in front of all of them. We have 4 states. And when we do the measurements, you see now that we roughly have 25% for each of the states. And that is what we would expect. So this is the inverse QFT, and it should not recover that state, but it should recover the state we started with. You can add classes now if you want to. So this variant of the same code attempts at making a more structured introduction to classes. So there's an initialization of the state, the QFT and the inverse QFT. There's a measurement sampling, and there is also a way to put out the qubit and input states, and it includes also state visualization and measurement visualization. So this is essentially the same code, but now with a class which is called Fourier Transform. It takes in the number of qubits and it sets up the number of states. It initializes the basis state, and in this specific case, it just initializes the state in the simplest possible way. It has a Hadamard gate here. It has a simple qubit gate. It has a control phase gate, the swap register, and here we apply, here we measure, and then we print the amplitudes. And this is essentially pretty close to what we had before. You can now plot the amplitudes. The next example here is a case where we plot the amplitudes, and it also allows you to have a superposition of the inputs. So the inputs do not need to be qubits which are not in a superposition or which could even be entangled. So this code also allows you to have an entangled state as the initial states if you want to play around with that. And in this specific case, what we have done is to create an initial superposition if you want to do that. And then it's also initialize a Bale state or GHC state. And the rest is the same as before. So there's a Hadamard, there's a single qubit gate, there's a control phase gate, and then the swap registers. And then we apply, we perform the measurements. We simply count the number of occurrences of a given bit string, which is then set up here. And then we print the amplitudes. And in this specific case, we could now rerun this with a 2-qubit case. And we want again to have, we could even take the first state as the basis state, which is the 0, 0 state. So if you run that one, then you will see now the amplitudes. So we get roughly, as we would expect, 0.5, 0.5, 0.5, because now the output should be a linear combination of 0, 0, 0, 1, 1, 0, and 1, 1. And the factor which we have in front of them, if we just switch back to the Jupyter notebook, now to the whiteboard, we will see now if we now apply this to the Jupyter notebook, no, sorry, on the whiteboard here, with 2 qubits, instead of having state 3, we could now think of having state 1, which means that if we do that, what we would have then would be a QFT of 2 acting on that state, which is the same as 1/2. And I'm not going to rewrite the matrix, so this is just the same matrix, but now acting on 1, 0, 0, 0. And we see then that when we perform the multiplication here, this will just give us 1/2 of 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. If we go back to the program, just to check that what we are getting is making sense, you see now that we have the amplitudes, which is 0.5, as you saw in the notes there. And if we then look at the counts which we do, we see now that for 1024, we should roughly have 250 in each case. And we see now that the bit strings, which we have set up, so this is 0, 0, 0, 1, 1, 0, and 1, 1, then you see roughly now that you're getting what you would expect from the mathematics. And this case where we simulate an experiment is actually the way we would run this on an actual quantum computer. And the more experiments we run, the closer we should actually get to a pretty equal share here. So we could try to rerun and do this instead of having in 2 in powers or something. We could now just set this to, let's say, 2000. And if we do that now, we see that with more measurements, we are getting closer and closer to 500 in each case. If we put the number of shots to 10,000, so let's just redo that. We see now that we don't get exactly 2,500, but we are almost there. And there will be deviations here, because now we're just measuring the probabilities of finding the system in a specific state. So when we make the measurement of the final state here, we see now that we are getting roughly what we expect. Now, in the next code, I've simply added some animations. This is something which you would need to be able to animate, but you can take a look at it. It's not so important right now. So what I wanted to switch over to now is something which is called the quantum phase estimation algorithm, because that makes use of the Fourier transform, the quantum Fourier transform. So the quantum phase estimation is actually a fundamental algorithm, and it's used to estimate the phase in eigenvalue equations of unitary operators. And when you have a unitary operator and an eigenvector, such that this relation here is obeyed, then the goal of the QPE is actually to estimate this phase phi. And this is a basic recipe by which we can try to get the eigenvalues of a specific Hamiltonian. And it provides a way to find this with a high probability. And it is a crucial subroutine for algorithms if you're dealing with many-body simulations, like we had in project number 1. Alternatively, for those of you who are interested in Shor's algorithm, this is an essential element to include in Shor's algorithm. So the algorithm itself is actually not that difficult to derive, but we need to go through some of the basic steps. So the basic steps are going to include a unitary transformation. We have an eigenvector of a unitary, and then the algorithm then, through the application of Hadamard's to an n-qubit register, we use a controlled unitary transformation gates to encode the phase, and then we apply the inverse QFT to extract the binary digits. So the number of qubits is going to be proportional with the floating point binary representation of the phase phi. So the more qubits we have, the better the precision which we are going to get for the specific phase. So we are going to define a little bit here. So the setup is going to contain a set of registers, which is this uppercase here. And then the second register is initialized to the eigenstate of this unitary transformation. So this could be qubits, which are then operated with a Hadamard operation. We have this gate operation represented by this unitary. And then we have an inverse, IQFT is an inverse quantum Fourier transform. And then finally, we make the final measurement in order to extract. So every one of these bits is going to represent the precision which we will get for the phase. And making these measurements, we can then reconstruct the final phase. So the mathematical goal is actually to estimate the phase phi, which then will live, since it's given in a binary float representation between 0 and 1, and where this exponential now is given by 2 pi I times phi. And the quantum Fourier transform of the n qubits is defined as we have seen before, where 2 to the n is this runs over all the many qubit states, and the QFT is essential for extracting the phase information. So if we think of the first step, which we need to do, we need to encode the unknown phase with a circuit that produces a result that is identical to the result of the quantum Fourier transform, which we have discussed earlier. And we are going to interpret the resulting qubits as parts of a binary fraction. So this number 5, which you see here, is now going to be represented as a binary fraction or as a floating point representation of a binary, where each qubit then represents a specific part of this binary fraction. So the more qubits you have, the better the precision. So if you have a 64 bits representation, 64 qubits, then you would get a precision to the 15 digits after the decimal point. So the inverse QFT is also essential because that is the one which is going to compute the phase. And what we are going to define then is, as you can see from this figure here, we are going to define a register which contains a given number of qubits, and where this given number determines the precision which we want. And like I said, with the QFT, we're going to interpret these qubits as parts of a binary fraction. And then we add a second register, which is the one you see here, which represents the eigenvector u of this unitary transformation u. And we can connect this register to a sequence of t instances, which are these ones. So if we have t qubits, then we would have t instances by which we connect this u. And each one is taking to increasing powers of 2, because we have this binary representation of the qubits. And similar to the QFT, then we connect this register qubits with, let me see now. Yeah, these are connected as controlling gates to unitary gates. And to achieve this power of 2, we're actually going to multiply this u with itself and accumulate the results. So the figure which you see here represents essentially the process. And let's take a look at the more detailed derivation of what we are going to need in the setup here. So let's now switch back to the whiteboard again. And let me fetch up my notes on this. We're going to switch back. By the way, if we don't get fully time here when we've gone through all the details, there are code examples on how you would set this up. There is a simpler code here, but I also added codes with Qiskit. And if we don't get time to look at all the codes, I mean, feel free to take a look. And there is also a penny lane example. And then finally, there is an example which follows what we discussed earlier. There's a QPE code without the explicit usage of quantum libraries, and where I actually look at a case where I can break down everything. This is a case with 3 qubits, and then I do the quantum phase estimation for that specific case. Let's switch back to the whiteboard. So if we look at the QPE algorithm, what we are going to need now is to set up some of the basic steps. The QPE, quantum phase estimation. So what we have is a unitary transformation. And that unitary transformation U is obviously a matrix where we have U, which is equal to U, which gives us the identity matrix, which also means that U complex conjugate transpose is equal to the inverse. So this matrix U has a set of vectors. So we're going to write it like that. So the column vectors here are orthogonal. And we know that these different vectors, so I'm going to put an arrow here to indicate that these are vectors and hopefully distinguish them from the matrix, which should be in an uppercase letter. So the U of I transpose times U of J is actually equal to a Kronecker delta Ij here. So this is one of the basic properties. And the matrix itself has eigenvalue, and we're going to show that. And the eigenvalue is lambda of I, e to the 2 pi of I multiplied with phi of I. So phi of I is going to be this eigenvalue, which we are looking after. And we know that when we act with a U on a vector U of I, this is going to be equal to an eigenvalue, which we just leave unspecified now. And we also know that when we now calculate the overlap here with a given vector U of I, and then perform an operation U with that one, U multiplied U of I here, then this has to be equal to this eigenvalue lambda of I squared. And we can just call this for lambda squared, just for simplicity. And we know then, due to the fact that these states are normalized, and we preserve the norm with a unitary transformation, we preserve orthogonality, then we know that this one, it means that the eigenvalue has to be equal to 1, the absolute value, which means that it leaves lambda unspecified with a face. And I'm just going to label this phi, instead of phi of I, I'm just going to call it phi. And this is an angle which lives between, or a value which lives between 0 and 1. So what we are going to do then is actually to set up a binary representation. And this is where the QFT comes into play due to this binary representation. So if we think of a binary representation in terms of a given number of qubits, in terms of T qubits, what we will have then is obviously that this state is now, or this value phi between 0 and 1 is now in a floating point representation of a binary number, is of a number which is actually between 0 and 1. This in a binary representation is given by phi 0, phi 1, up to phi of t minus 1. And for those of you who are not familiar with the way we represent numbers in a computer with a binary representation, this is going to be equal to phi 0 times 1 divided by 2 to the power of 1 plus phi 1 of 1 divided by 2 to the power of 2. And this continues all the way up to phi of t minus 1 of 1 divided by 2 to the power of t. So the t bits which we have, they represent the precision we want for phi. And if we have a standard binary representation of a floating point number, then we know that if we have 32 bits, this will give us a precision in the decimal representation to the 6 to the 7th digit after the decimal point. If we have 64 bits instead of 32, what we normally call double precision, then we know that when we transfer this into a decimal representation of decimal basis, then we have something like 15 leading digits after the decimal point. And that will be the precision of the calculation which we will have. So let's look at an example now and how we can actually set up things. So let's start with t equal to 1. So we have just one bit. So that means that with t equal to 1, then this lambda is going to be represented to a given approximation as phi 0. Now phi 0 is actually 0, 1. Is a binary, so that takes values 0, 1. And that clearly means that the value of phi, since this takes values 0 and 1, we see immediately from the formula which we put up here for the representation of a number in the binary representation, then we get either if phi 0 is 0, we have 0. If phi 0 is 1, we just get a half. So there are only two possible values. So it means that phi is going to be either 0 or 1/2. So clearly, the more qubits I place in, and if you now look at the examples which I've put online with either Penny Lane or my own code examples or the Qiskit examples, the more qubits you have, the more likely it is that you will get a good representation of that specific eigenvalue. Some of the examples run with only 1 or 2 qubits, and then you will see that the value of phi is equal to 0 in those examples, and that's simply because we have just too few qubits to represent a given state here. So that's pretty obvious. And in one of the examples, we have an original eigenvalue, which is 1/3. And in the cases with just 1 or 2 qubits, if you run those examples, you will essentially just get a result which is equal to 0 in some of the cases. So the basic assumption we are going to make now in setting things up is, or the basic recipe which we need to think of is, one, we need to initialize t bits, and these are normally initialized to 0. So we would then set them to the state 0. So this is what we normally call the first register, and that's the one which we're actually using to extract the final information about phi. Then the second register contains all the bits which are needed to define the state we actually want, the eigenstate which we want to reach. All the bits which are needed to define the state which we're looking after, whose eigenvalue we're actually looking after. So let's just call that x. So when we are setting up a drawing here, if we now have a case with just 1 qubit, so we would initialize that with 0. So this is now put into a linear combination through a linear superposition with a Hadamard. And then we have this bit x. Now here, we have a unitary transformation for this specific system, like that. This produces a new state, which we would label as a psi1. And after this is this specific state, and after this unitary operation, we produce a new state. We just do it like this. And this new state is a psi2 here. And then we perform a new Hadamard transformation. And then we can proceed. So let's just write down the operations which we are plugging in. So we would have a psi1 here, which is going to be given by this Hadamard operated qubit. And then it's given by the tensor product with this state x, which we have left unspecified. And then we have plus 1 times this state x. And then we have this control U operation. In that case, we get this new state, psi of 2 here, which is given by 1 over square root of 2. And then we have 0. Now, this acts only on the qubit with value 1. So this is going to be given by e to the 2 pi I. And then we have 0 of phi 0 multiplied with 1. And this is then tensor producted with x. So that's the next state. And we can actually rewrite this as 1 over square root of 2, and then 0 plus e of 2 pi I of 0 of phi 0, and multiply with state 1, and then tensor product with x. So when we measure, so measuring either the state 0 or 1, that gives us a probability of B of 1/2. So if we now take and perform a Hadamard on this specific state, H, no, psi2. So if we take H times psi2 here, this will be the state psi3. And that will give us 1/2. And then we would have 1 plus e of 2 pi I of 0 of phi 0 multiplied with 0. And then this has an additional term, plus, and then I have 1 minus e of 2 pi I of 0 of phi 0 multiplied with 1, and then tensor product with x. So phi 0 is either 0 or 1. So if phi 0 is equal to 0, then what happens when we now perform the measurement, then phi 3 is equal to 0, as it should, because we have then that if we now look at the operations here, if phi 0 is equal to 0, then this term just disappears because it's 1 minus 1. And here we get 2 divided by 2. So that gives us a factor of just 1. 1 times 0 plus 0, and then tensor product with x. So if phi 0 is equal to 0, when we perform this measurement on that first qubit, then if this phi 0 is 0, then we know that the state phi 3 is equal to 0. And if phi 0 is equal to 1, then we have that psi 3 is equal to 1. So that means that if we measure either 0 or 1, with a certainty. So we would have to repeat that many, many times to see how many times we measure the states. Then this phi angle is equal to 0 or 0.5. So if we summarize this, if we measure phi equals 0, if we measure with certainty zero or 1, then phi is equal to 0 or 0.5. And then we know the value, we know the eigenvalue. Value since lambda is equal to e to the 2 pi I multiplied with phi. But then we get an answer which obviously is defined by the precision you get from just having one bit. Now, if you go back here a little bit and look at the graph we made, there's a reason why we have just a Hadamard gate here. The reason why we have only a Hadamard gate here is that we have only one qubit. So your Fourier transform is then given for one qubit. Your Fourier transform reduces to just a Hadamard gate. And the inverse of a Hadamard gate is a Hadamard gate. So this is what the circuit would look like if we have only one qubit and we are making a measurement with a precision which then is just equal to the precision we get with one qubit, with one bit, sorry. Which again means that the result will then simply consist of two possible answers, either 0 or 0.5. Now we can become a little bit more ambitious now, and we can move on. And instead of just having one qubit, we could have two qubits. N equal to 2. And that means that the possible values which we would have would be 0 of phi 0 and phi 1. And that means that if we now go back to the recipe which we had and look at this specific recipe here, then we know that these numbers would then give us a phi 0 divided by a 1/2, multiplied by 1/2, plus phi 1 multiplied with 1/4. So that means that what we would get then are a little bit more possibilities, so we can have a higher precision. So we would get phi 0 multiplied by 1/2 plus phi 1 multiplied by 1/4. And then we remember that phi 0 and phi 1, they take values of 0 and 1. And now we are getting a little bit more possibilities. So if phi 0 and phi 1 are 0, then clearly phi has to be equal to 0. If phi 0 is 1 and phi 1 is 0, then we get a half. If phi 0 is 0 and phi 1 is 1, then we get 1/4. And then finally, if both of them are 1, then we get 1/2 plus 1/2. So the next value which we can reproduce is actually 3 divided by 4. So that means that we will have a precision which is described by 2 qubits, and the 2 qubits will then give us 4 possible values. Then clearly, if we keep increasing this, we will get more and more values, and the distance between the values will become smaller and smaller. So in this specific case, if we are thinking of a scale from 0 to 1, we will actually have 0, we will have 1/4, we will have a half, and we will have this value, but we will actually not get 1. So the type of values which we get depends now on the number of qubits. So when we have 2 qubits, then we would need to apply these controlled operations on all the qubits. So 1 on each qubit at a time, which again means that if we now go back to the Jupyter notebook, we can set up the basic algorithm. So let's do that before we stop today. So if we go back, so what we would need then, if you look at these operations here, so these operations would now be represented by such controlled unitary ones acting on each qubit at a time. Then when we've done that, we will perform an inverse quantum Fourier transform, which now will include, if we have 2 qubits, it will include 2 Hadamard gates and a controlled S gate. And when we've done that, we would then perform the measurements on the individual qubits. And when we have the measurements, then we find the values of the given qubits. So the mathematics here is that we are going to set up the initial state, as we discussed earlier. So if we now have n qubits, we need to perform the tensor products of n qubits. And then we have the second register, which then corresponds to the number of bits which we need to represent a given state. Then we apply a Hadamard to the first register to create a superposition. The next step is to perform the controlled unitary operations, apply the operation with exponential powers. And for the eigenstate, then this actually becomes equal to this expression, which you see here, because with the eigenstate, this picks out, if this is now a unitary transformation acting on the state, it picks out the given phase factors here. Then we apply the QFT to the first register to transform back, and where the coefficients are peaked near the values of 2n/5. And measuring the first register gives the n-bit estimate of 5 with high probability. And this is essentially what is included in these codes. So you will now see a simple implementation of it, where we are not setting up. This is a very simple code. So we have a Hadamard, we have the QFT operation, we have the inverse QFT, which simply takes the QFT operation we have here. And then we have a controlled unitary here, which is then applied to the state. We apply the gates, so gates times state. We perform a measurement, calculate the number of states which we have, and then we simply need to define how many qubits we have. So the QPE here simulates the quantum phase estimation algorithm. So the total number of qubits is set up here with the number of states. We initialize it to the state 0, so the first state. And then we have the Hadamard, the controlled U operations, and then apply the inverse QFT. And finally, we perform the measurement. And in this specific case, when I set up phi equal to 1/3, then this is the result I want to have. So if I have, let's say, if I take only 1 qubit here, this is not going to give a very impressive result. And you see, I actually get 0. That's the estimated phase. So I would need to add many more qubits to get something which would be meaningful here. So let's try with 4 qubits and see if that gives something meaningful. Still, we're getting lots of zeros. So this is a fairly tricky value which we need. So we would have to increase the number of qubits in order to perform these calculations. And this is something which will take much more time, as you can see here. So it's still running. Now, one of the things you see immediately from this very simple code is that as soon as we increase the number of qubits, the code is running much, much slower. And if you compare that with the VQE, it's pretty obvious because we have to perform all these Hadamard transformations. We have to perform all the unitary controlled operations. And then at the end, we have to perform the inverse quantum Fourier transform. If you think of the VQE, the only thing we did then was actually to transform a Hamiltonian in terms of specific X, Y, and Z gates. And when we had that, depending on the number of particles we had, we need a certain number of qubits. Then we could actually set up. So this is actually, I'm just running this as this kind of bad example with 10 qubits. This is simply because this will take us a lot of time. And you see now it hasn't yet reached any conclusion yet. And it's actually going to run for quite some time here. But the whole wisdom which you get with the QPE is that it's a very nice algorithm, but it becomes very inefficient when we now want to run it with many qubits. The codes here contain also examples with QPE with penny lane and Qiskit, and there are also at the end here some discussions of applications with so here's a more general code, which also includes swap registers, etc. And in this specific case, it actually runs through and estimates. Now this is going to be a little bit slow. Let me stop the other code which I had here, because this is still going to be running. So let me stop that. And let's run the last code here. So this is an example with 3 qubits, and it just gives you the bit string because now you have 8 states, and it simply tells you the one where you have most measurements. You would have to repeat this many more times so that you get one of the specific state which peaks out. Now, in the lecture notes here, there's also some general motivation about Shor's algorithm. I will just leave that as a reading background for you. In Hunt's textbook, there is also in chapter 6.6, there is a discussion of Shor's algorithm for those of you who are interested in it. But we will not have a lecture on Shor's algorithm itself. But it's an algorithm which actually is extremely important. It's a algorithm for integer factorization, and it efficiently factors large integers and by using quantum period finding. And it has an exponential speed up over the best known classical algorithms. And it actually breaks the standard RSA encryption. So the code or the algorithm is based on quantum Fourier transforms and the QPE algorithm. But we will not discuss that in the lectures. But I know that there's some of you who are interested in using that. So next time, we are going to dive into quantum machine learning instead.